Hello, everybody, and welcome to another edition of WAVY Science Lab. I am meteorologist Jeremy Wheeler, and we are going to be talking about some cool stuff today. We're going to be talking about the layers of the atmosphere. And, when you're in grade school, you learn about these things a little bit, but you might not necessarily go into much detail. So you may know there's 4 layers of the atmosphere or more layers of the atmosphere, depending on what aspect you look at. But yeah, we're going to go into some of the details on some of this, deep dive into those different layers. So let's take a look at it. And basically, the layers of the atmosphere, it's, just like an onion, right? It's got layers. Onions have layers, ogres have layers, and so we borrowing from Shrek, and so the atmosphere also has layers, and so let's take a look at the first off the kind of the pressure. I did a whole episode on pressure, but I do want to talk about it a little bit just right here how it fits into these layers. So as you go up into the sky, you've got basically the different layers of the atmosphere, right? So if you go up in the first layer, the pressure decreases. Well, really, you keep going up, the pressure decreases in all of them, but it gets down pretty low even in this lowest layer. And so the pressure decreases. So on the left-hand side there, you've got the millibars, and the millibars of pressure. And so these millibars of pressure, it's a unit. So sometimes we'll talk about hurricanes, and it was got down to 900 millibars. It's the lower the pressure, the stronger a storm is usually. Well, in this case, the pressure decreases with height, and so you can see 1,000 millibars at the surface. That's an average. Sometimes a little more, a little bit less than that, and so that's the lowest layer. And then you go up, you get up to there's Mount Denali in Alaska, 20,000 feet. And so now you're hitting about 500 to 400 millibars. The jet stream is usually about 300 millibars on average. And that, is up or down a little bit. It's not, a locked in thing. Also depends on the temperatures below for the layering and things like that, the height. But you can see the plane flying there about 30 to 40,000 feet. So up there is about 200 millibars, and then it goes down from there. So the humidity also decreases with height, but definitely the pressure decreases with height. So let's get into that's really the lowest layer. That's in the tropopause, or troposphere rather, troposphere. So and then the pressure decreases even more going above that, but that's already down to just 100 millibars versus 1,000 at the surface. So this troposphere, it's the bottom layer, and it's you can see here it's got a lot of stuff here. So the surface is 33,000 feet, give or take. It's the lowest layer of the atmosphere, and contains 99% of all the water vapor and aerosols in there. So most types of clouds form here, and yeah, a little bit forms into the stratosphere, the second layer, but most of them form here, and it's where almost all the weather occurs. So, when we talk about, thunderstorms, things like that, this is the layer that happens. So, temperature and pressure decrease with altitude. So, but that's just in this layer, just in the troposphere. It's where about 75 to 80% of the atmosphere's mass is. That's really interesting, isn't it? I mean, you think about it, that's the bulk of what goes on is in that layer, in the bottom layer. So everything's dense, everything's compact. To a degree, but I mean, containing 99% of all the water vapor and aerosols. That's a lot. I mean, that's almost the entire atmosphere in this one layer, but it only goes up to 33,000 feet. So it's compact. There's a lot in there. All right. So the height of things, just kind of comparing here, Mount Everest, the tallest mountain above sea level, about 29,000 feet. And then the tallest building in the world, the Burj Khalifa, Dubai, 828 meters. So that's 2,716 feet and 6 inches. And jet fly average 30 to 40,000 feet. So that's 5.6 to 7.6 miles. So just kind of give you kind of relatively where things fit in here in those lowest layers. Now in the troposphere, you've got differences in pressure, differences in temperature. So I like to think about pressure as a column above our heads of air, right? A column of air above our heads. And so some of these columns are colder than others. So you got one here one's colder, the other one's warmer. And so when that happens, it's more dense and it's compact. And you notice there's a difference there in the top. that there's a difference. There's some mass on one, or no mass or very little mass above the colder one. And so what happens is that the air wants to go and push from the warmer above to the colder, because there's more air, less air, and so it creates a pressure difference. And so what happens is that air wants to rise and go, well, not rise, go towards the warmer to the colder aloft. But then when that happens, the air will take a bend to the right because of Coriolis force. And so we've got that warm air trying to, the wind's trying to push north, but it gets bent to the right. And so this creates the jet stream, this effect, up, close to the top of the troposphere into the stratosphere. So we got the jet stream there, and your warm air moves around, your cold air moves around, the jet stream moves around with it. So this is how weather systems move. And then areas of low pressure will track along that. So now we're at the surface, and we got high pressure to the west, you got an area of low pressure. This was a somewhat recent map. And we had some weather, wintry weather, all kinds of it. So then, in area low pressure, air rises, and then air sinks when it comes to high pressure. So this is all in the troposphere. Now, you can see that, they're usually bouncing around on these maps all over the place. The areas are high and areas low pressure. And then you've got fronts at the surface as well, the very lowest layer of the troposphere. They do go up to a certain height, several thousand feet, but then fronts don't really get too far up. But thunderstorms, the base of a thunderstorm is about 5,000 feet. And that's give or take. I've seen them when it's really humid out. Let's say middle of summer, you got, air saturated. It can get as low as 1,000 feet for it to start. But then the tops of it get up to about 30 to 40,000 feet. And that's on average. I've seen them, some big thunderstorms get up to about 50, 60,000 feet. So that's, we're talking about the second layer of the atmosphere. And so what happens is they can survive these thunderstorms because of the, you got rising and sinking air. But in the upper levels, your rising air will get cut off if it goes, straight up or straight back down. So you have wind shear for a thunderstorm to kind of perpetuate. All right, so we've got the thunderstorms, the cumulonimbus clouds here, and you can say it says it gets up to about 40,000. I've seen them even higher. In the strongest thunderstorms, out in Texas, Oklahoma, I've seen them get that big. Here, I think 40,000 is a pretty good average. And then you've got the different cloud types in there as well, which we had a whole podcast on that. So we're going to go into a little more detail on that coming up in just a little bit. So we're gonna maybe not go into clouds so much, but we're going to start to get more into that second layer. All right, stay with us. All right, we are back, and we're talking about the layers of the atmosphere. I'm meteorologist Jeremy Wheeler, and so far we've just talked about the first layer, but now we want to try and talk about the other layers of the atmosphere. So those clouds, all these clouds are within the first layer, but you got the shooting anvil, the over top of the thunderstorm, that does get up into the stratosphere. And then there's another type of clouds called noctilucent clouds, which get up even higher. But so let's talk about, first off, the layer in between these two layers, the troposphere and the stratosphere. There's a pause. Notice the temperature cools down up to a height, and then it stops cooling. And then it doesn't change much going up with height. That little line there, the blue and red line, the blue and the red line. So what happens is there's a pause, and so it's a tropopause. And so this is around 36,000 feet, give or take. And it's a layer between the troposphere and the stratosphere. The temperatures are constant with increasing altitude. So there is some warming there. There's warming. And sometimes it increases a little bit too. It's not, I don't think it's a solid, isothermal. I think the temperatures do increase a little bit. Temperature around minus 60 to minus 76. And this acts like a ceiling for the, this acts like a ceiling for the weather, the thunderstorms. They can't rise above that. And so that's important, because what happens is these, little parcels of air like to go up to a certain height. So we think of it like this, these little parcels in here, and this is a Galileo thermometer, by the way, these parcels rise up. And so if the parcels in there are warmer than the surrounding environment, then they'll rise. It's unstable. But if they're not as warm, if they're cooler than the environment, then they're stable. They won't go up any higher. And so if the atmosphere warms, those parcels end up becoming cooler than the surrounding atmosphere. And so then they stop. So there's kind of a ceiling there, at the tropopause for things to rise. And sometimes, it depends too, because if it's really warm below, like in the summertime, those heights will change, so you can get higher heights because of that. So anyway, very warm, humid air mass. So let's go back to that. And so this is where the jet stream and the turbulence are, typically where aircraft fly as well, the tropopause. All right, so the ozone is the source for where the heat comes from. So the ozone layer, we're familiar with that. There's another layer. Most ozone is concentrated layer in the stratosphere between about 9 to 18 miles above the Earth's surface. And I think it's a little below that as well. But the ozone, O3, absorbs UV radiation, especially UVB radiation, and this releases heat. So you get 2 ozone molecules plus UV yields 3 oxygen molecules plus heat. So there you go. It converts it. But it does protect us, right? So the ozone layer, early 1970s scientists concerned about pollution. They learned about this, the ozone layer a while back, but they were starting to get concerned because there's these chemicals in there that could actually destroy ozone. Chlorine and bromine can destroy ozone. Chlorofluorocarbons, we've kind of, many of us have heard about that. And so then, we don't. That's bad. And then methyl chloride, carbon tetrachloride, and ravens with lasers. So they will destroy ozone. Now, the Montreal Protocol was finalized in 1987, and this was an agreement for countries to reduce ozone damaging chemicals. It was ratified by the U.S. in 1988, and chemicals were used in refrigerators, air conditioners, fire extinguishers, aerosols. And so, it took a long time for those pollutants to get up there, but once they did it, they lasted for a very long time. And they could actually measure this stuff in the atmosphere. They could go up with a plane and measure, and they had. So they found that there was a hole in the ozone layer, but because of the Montreal Protocol, it's been getting better, but it hasn't, gotten fixed right away. So this is kind of a timeline here. You can see 1971 was already decreasing. I think 1980 there was a lot of attention to this. I remember that when I was young. We learned about it, and because it was becoming a problem, and then eventually the curbing of all the CFCs, the carbon fluorocarbons, and the pollution. Now it's starting to heal. It's starting to come back. But you can see, we're in 2026, and it's on the up and up, but it's a slow climb, and it will get better eventually. That's the forecast, going to 2041, 2065. But it's still there. That ozone layer, it's not gone. All right, so now we're getting into the next layer, the stratosphere. And so this is 6.2 to 31 miles. Second layer of the atmosphere. Weather balloons fly up to this point, and then usually they pop or they deflate. Very dry air. There's very little water vapor. It's stable air at that point because your air's, the temperature's rising, or it's isothermal for a bit, but then it's rising, and that's because of the ozone layer. Temperature increases with altitude. So the upper boundary is called the stratopause, and the lower boundary is called the tropopause. And so again, more layers in there, I know, but the main layers are the spheres. The troposphere, stratosphere, mesosphere, which go into the pauses are the boundaries between those, and they're thinner. All right, so there's another view. Again, we talked about the first 2 layers now, and a lot happens in that troposphere, so we talked about that quite a bit. But some things happen in the mesosphere too, in the other layers. Mesosphere is the third layer, mesosphere. Sprites above thunderstorms, those little bright lines, that happens. And I'm going to do another podcast on that whole subject. That weird lights and things like that. Meteors burn up in the mesosphere because it's thick enough for the first time for them to do that, and noctilucent clouds as well. So here's the mesosphere, and it's the third layer where most meteors vaporize. There's a higher metal concentration, I guess. Temperature decreases with altitude, and so now we were warming in the other layer, the second layer. Now we're decreasing again, and this is where the coldest temperatures of the atmosphere, minus 130 degrees Fahrenheit. Which you would think, well, doesn't it keep cooling? Maybe not so much. Let's talk about it. So let me back up here a little bit. I want to show you the layers again. So remember, again, this is the temperature. It cools with height in blue up to the top of the troposphere, then it warms in the stratosphere, and then eventually that heat dissipates, right? It can only go up so high, so it dissipates, and that's why you start cooling down again in the mesosphere, and it thins some more too. It gets even thinner. So this is 31 to 53 miles up that mesosphere. All right, so the mesosphere, here's just kind of that summary again. Third layer of the atmosphere. And then above that is, of course, the mesopause. And then you've got where, the temperature starts changing again. And then you've got the thermosphere in the next layer. All right, so the thermosphere is 56 to 300 miles up. And it's the layer below the exosphere. Exosphere is about 440 miles up, but we're not going to talk about that too much. We're running out of time. We're going to take a pause here, and then we're going to talk more about the thermosphere, and then we got some other layers that we're going to fit in as well. All right, stay with us. We're back, and we're talking about the layers of the atmosphere. Took off my sweater; it was getting a little warm, so took that off. And now these layers of the atmosphere, we talked about 3 so far. We got up to the thermosphere, and this is the layer below the exosphere, right? So this is kind of the top layer now. We're getting into the 4th layer, and it's considered outer space, basically where the ISS and satellites orbit. Very low air density, and it's separated here a little bit. I'm going to talk more about that when I talk about some different types of layering here, the atomic oxygen, nitrogen, helium. The temperature increases with altitude now, so that's different. Now we're starting to warm things up again. And the temperature is strongly influenced by solar activity. That's where a lot of the heat comes from in this layer, because not from the surface anymore. That doesn't reach up to this level. I don't believe it does at all. But now it's influenced by solar. So thermosphere again, 56 to 311 miles up, and I don't know, I would even think higher than that because the exosphere, what I've read, was 440 miles. But I think there's a little disagreements in exactly where some of these boundaries are sometimes when it gets to the upper levels. But basically, let's just say, okay, 56 to 300 miles solid. And then above that, well, a little gray area. But yeah, the line turns red and it goes up. So there's heating with this in the thermosphere. All right, so in the thermosphere, heat comes from the high energy particles collisions. But there's not a lot of particles up there. It's less dense. The temperature can reach 932 degrees to 3,632 degrees Fahrenheit, which is much, much hotter during the day and during high solar activity. That makes sense, doesn't it? I mean, you've got the daytime temperature a lot hotter, the sun hitting it, and then, nighttime, there's still some particles up there getting hit, but not nearly as much as when the sun's directly shining down on it. And the space shuttle, ISS, most satellites orbit here as well. So temperature versus heat. Now, I've talked about this in the temperature podcast. Heat is the total kinetic energy in a system. The temperature it involves how much substance there is as well as the energy. So this is key to this layer. The temperature measures the heat, but how well does it represent that heat? And we did the experiment, which I always bring back. Frankie the Snowman, thank you so much. You really, you're the best. So then when we got the oven, we're heating up those particles and they're bouncing around, right? So, but we said, well, if you've got a lot of particles, well, let's just say we have the particles, there's a high temperature there. They're bouncing around. There's a lot of energy, a lot of kinetic energy, but maybe we only have a couple of particles in the oven. Maybe that's it. Maybe there's only 5 in there total. Well, in the higher parts of the atmosphere, the particles are bouncing around, but there's not a lot of them. There's such a low density. So it's a high temperature, but it's not a lot of heat, if that makes sense. Hopefully it does. So now we're starting to get into the heterosphere versus the homosphere, because now there's also a different composition to this thing. And so this is within the layers that we just talked about, the 4 layers. This is within them. But it's kind of how the atmosphere separate a little bit. And so the composition where the atmosphere is different, the first layer, the homosphere is surface up to about 80 kilometers. So in that layer, the composition is mainly the same aside from ozone. You've got the ozone layer in there, right? So that changes within that. But up to about 80 kilometers, you've got kind of, you could take a sample and you'd hit about the same ratio of the molecules and all that. But once you get up above that, then it's called the heterosphere. Then the layers are composed of different elements. They vary in height by molecular weight. So the hydrogen is light, and that's way up there. And then in the lower levels, you have more nitrogen, more oxygen. It's not a sharp cutoff for this. I mean, it's kind of a continuum, but basically that's what's going on. Now you got the heterosphere within that. All right, so then you've got the ionosphere as well, another layer. Yep, another layer. Wow, there's lots of layers. So this ionosphere is between 80 and 600 kilometers. Extreme UV and X-ray solar radiation ionizes atoms and molecules, and that creates a layer of electrons. And this affects radio waves, GPS, satellite communication, and you get the auroras happening in here as well. So you've got the auroras forming. You got the sun out there, the magnetic field. We had a whole podcast on that too. I know I've done a lot of podcasts, haven't I? And so you've got the magnetic field there. And so these particles come in. And so the charged particles and protons are emitted from the sun, and they go around that magnetic field, the Allen belt. Well, eventually they like to take that path because it's a pole, and so they'll be attracted to and go towards the poles and enter the Earth's atmosphere through that point. So then the electrons collide with the molecules in the atmosphere, and the high energy creates that excitation and light, right? So the light is released. So the resulting excitation of these collisions cause the varying colors based on the height and type of molecules hit, word for word. So there you go. And then you've got the different colors in there of the auroras as well. And so I'll actually probably do a whole other podcast on this along with the lights. And so you get the pink auroras, nitrogen molecules, the red auroras are atomic, green is oxygen, and the blue is nitrogen. And we saw, because you got the heterosphere, it depends on what height that's hitting, whatnot. So pretty neat stuff. I mean, it is really cool stuff. And then here's a good example from NOAA of aurora, and we've seen some spectacular shows. Here's another one in our system, and up north you can see the really brilliant lights and everything, and I'd love to go see that. But I think I only saw it once when I was a kid in Illinois, where it was just a greenish hue. It was very light, you could barely tell. But a lot of times around here, lately, we've had a lot. You can just see kind of a reddish hue, and most of the time, only when you take the picture and see it later, you can't see it naked eye. But once in a while, maybe we'll be able to. Who knows? At some point in there, maybe we'll be able to, get it to where we can see some of these brighter auroras. But that'd be a pretty bad magnetic storm, so maybe we don't want that to happen. We get communications disrupted, things like that. We wouldn't want that, would we? So it's give and take. But I would love to go and see the northern lights and go up north on some occasion. All right, so then the last thing, last but not least, the environmental tip of the day: make sure your appliances are up to date. Especially when it comes to refrigerants and CFCs, things like that. They shouldn't be in there anymore, but there's still some of the things that they replace the CFCs with. Still, they found out aren't so hot. So I mean, make sure that you're up to date. You're on your appliances. Dispose of old appliances responsibly. Make sure that they're recycled in a proper way, and limit aerosol usage, because they still use some bad things in there. Maybe not the CFCs anymore, but they still use some stuff that's not so great. All right, so that is it for today, folks. Hopefully you learned something about the atmosphere and the layers of the atmosphere. All right, everybody have a good day and keep learning. And this is me from WAVY Science Lab.